Yeah, so good morning, everyone from Lithuania, Vilnius, and welcome to the second seminar on laser micromachining applications organized by Toolas cluster. This time we will focus on photovoltaics and semiconductor industries. We will look what needs do we have, what is the situation, and we'll see how their needs can be solved by laser micromachining technologies. And I am coordinator of laser micromachining cluster Toolas, and together today I will moderate this event together with Tadas Lipinskas from Toolas member Optogama. And before we jump to our interesting presentations, we will have a short intro of Toolas cluster delivered by Tadas. So Tadas, please share your screen.
Okay, good morning, everyone. Do you see my screen?
Yes.
Okay, so just a few slides about the Toolas cluster. So this cluster is based in Lithuania, in Vilnius, and at the moment it's uniting laser industry experts from 10 companies and institutions. And all these companies are working in the field of laser micromachining, including photovoltaics, semiconductors, glass processing, and others. Cluster members has more than 20 years experience in this laser industry, 35 patents, and constantly investing into R&D. So we are one of 3 hubs working in the field of photonics in Lithuania. At the moment, cluster partners are running more than 20 projects. Most of them are international and some of them are national. And recently we started to build our new R&D center. And until the end of this year, we expect to have new premises for production, for R&D, and to serve our well-known customers worldwide, as you can see in the slide. In the laser micromachining cluster, we have companies covering the full value chain, starting them from manufacturing components. Then we have companies making laser beam delivery systems for integrators. We have company Tadas Tech working with the infrared and thermal vision, including some vision systems for micromachining in infrared range. We have metal workshop companies. We have companies developing software for laser machines. We have optical engines and technologies manufacturers, as well as laser machines manufacturing. And some of the companies like Workshop of Photonics, they are providing services for laser micromachining and development and some small scale manufacturing related with the glass cutting, micromachining of glasses, some semiconductors, etc. So if you have some issues that laser micromachining could solve, you can contact Maria directly. He will put in contact with the right person, and we will try to serve you with our competences, with our expertise, and we would be glad to help to solve your current issues. So thank you very much for your attention, and have a good discussion today. Maybe you have some questions, yeah? So please ask.
Yeah, I see Chris is clapping. It's not a question, yes? Mm-hmm. Okay, so thank you, Tadas, very much for this nice intro of our cluster. And now we will hear 5 thematic presentations. Each presentation will be followed by 5 minutes Q&A session. And I really encourage you all to raise questions if you have. You can write them in the chat, you can raise your hand and we will ask you, or you can just speak up in the questions time. And if there won't be enough questions, I hope Tadas Lipinskas will help us to boost some discussions. And now, to begin our seminar, I would like to welcome Dr. Juras Ulbikas, Director of Modern E-Technologies, who is also representative of Lithuanian Photovoltaic Technology Cluster. And he will give us a background of photovoltaic sector developments in Lithuania. So it will be a great intro to our seminar. So Juras, please, the stage is yours.
Okay. Is everything fine? Okay, you are seeing my presentation?
Yes.
Okay. Let's say my idea for the presentation was to show how much innovation is influencing, let's say, competitiveness of our producers and in general PV sector. Therefore, well, focus will be more on innovation than on other things. Let's say I would like to start pointing out that today photovoltaic is the most green and cheapest source of power in the world. I hope you all aware about that. And I just put two examples about prices which are coming down permanently for PV products and market growth. Actually, it is a well-known fact that PV overcome fossil fuels investments in recent years for the building of new facilities for power generation. What we are doing in Lithuania with PV. Actually, we established cluster somewhere in 2008 by initiative of researchers and industry. Okay, in this time it was not industry but investors going into PV business. And through these years, we have seen significant, let's say, transformation in strategy of the cluster and cluster industries. Actually, when we started, PV market was really growing fast, about 30% a year, and it was highly profitable. And cluster strategy was to start this sector in Lithuania through new manufacturing facilities, both in solar cells and modules. In parallel, it was clear to everyone that we need also R&D infrastructure, which will support our industry with innovation flow from R&D environment. Today, market in recent years, we also facing the same growth of PV sector in the world, but it's really changed significantly. Today, it is very low profit and is dominated by China producers, leaving something like less than 1% of production in Europe in general. Therefore, I would say proudly that we not only survived during this shift, but also we are growing. We are opening new companies and new facilities for production. Why? Just because our cluster strategy is specific. We are working in profitable market niches, which are with highly innovative products and which can be sold with regular or high profit margins. It means to us, R&D driven growth is a must. Let's say short overview what innovations we faced during this time. Actually, just as example, solar cells, production technology upgrades. Actually, solar business in Lithuania started from investments in different technologies, which one of them was based on so-called flex cell technology and was developed by Lithuanian R&Ds, joined forces from different groups. And in parallel, we had development of standard technologies, aluminum back surface field, solar cell technology, and 3-bus bar model. It came Solitech to this technology. And Solitech, through this years, had transformations in their technologies even 3 times. They moved fluently to PERC solar cell technology. And after that, now they are started producing IBC solar cell technology with multi-bus bar IBC module technology. It's, let's say, as you see, each few years, we need a significant aggregate of facilities just to keep pace of this fast-growing technological business. If about positioning where we are in comparing with silicon value chain, I would say we are having only few segments of this value chain. It means we still have solar cell production, solar motion model, and now it's moving PV project developers and other partners which are doing the field business in the field, developing PV plants. It means we are not touching early stages of production, starting from polysilicon, ingot, wafer, and other materials which are essential part of PV systems. Back to basics on silicon technology. I'm not touching thin film. I noted that in the other presentations they will be covered. Therefore, I am just trying to focus on technology which is available in Lithuania. Let's say if talking about solar cell, it's quite easy device. It's the largest diode in production in the world. It means when you are having wafer of silicon in semiconductors business, you are producing enormous number of microchip from one wafer. Here, you are producing single diode on the whole wafer. And it is just few technological steps to produce such device. Okay. When we are shifting to silicon solar model, it is let's say a sandwich of several simple materials with connected solar cells in between. I'm just putting what does it mean, but I don't think it needs to be explained. It's quite simple. As you see, solar technology in general is very simple technology, and still there are enormous potential for innovations to improve quality and performance of these devices. I would like to stress on one, let's say, as we are talking about lasers, I want to show you example how lasers can be used in silicon technology. I was mentioning this technology in the earlier slides, and it was investment of our industry to build a factory based on completely novel technology, two novel technology as it appears in the later stages. It means we started from self-aligning copper contacts, built equipment for copper contacts deposition, and we were supposed to move to large-scale silicon solar cell production. What difference with standard technology? As you see, we were able to demonstrate higher quality, lower costs, and let's say possibilities to produce with less use of argentum. Okay, it's silver, and have quite high quality devices. We stopped with this technology. Here you see laser process equipment, which was developed by a Lithuanian company. As you see, it's it was using femtosecond laser, quite innovative approach. And on this grooves, it was possible to grow extremely narrow in these times, down to 15 microns contacts, which were helping to get higher quality of solar cells. It was supposed to replace some parts of standard production line when all contact related process steps were replaced by laser processing and nickel copper electroless plating deposition. But actually, we were able to demonstrate efficiency, repeatability, homogeneity, good capex and opex, but we failed with scalability and throughput to go into higher numbers of cells per hour. It means we stopped on TRL 7 level, and this technology, okay, failed to come into the market. This is why I was talking about this example. I would say that we need to be very careful with innovations we're choosing. We need to analyze innovation capability to meet all this commercially important segments and points, and only this way you can attract really high investment from investors into your technology if you are putting on the table any kind of innovation solution. Okay, and this is all I would like to go through, and I would like to finish with one simple sentence. Solar technology needs innovation. It's, to my understanding, in the very early stage of what is needed to be done. And as an example, I would like to point to you an attention to long time ago written book of Arthur Clarke. I hope you know this science fiction author. And in his famous 2001 Space Odyssey, you can find, let's say, a device which is our future. It means 100 efficient solar energy converter, which is able to convert on all wavelengths, all energy into useful energy for you. Today, we are at the level of, let's say, something 25% of efficiency. Then it is only quarter of capabilities we need to have for converters. Okay, this is all I want to say, and thank you for your attention. Questions, please.
Thank you very much for interesting presentation. Now I'm really engaged to read the book. I saw the movie. I love it, Space Odyssey.
Yeah.
And now I see Egidijus has a question. So welcome, Egidijus.
I have two questions. One of them is, do you plan to use somehow black silicon option for the cell manufacturing, and do you plan some perovskites material for solar cell?
Yeah. Okay. First question, black silicon. Actually, in flex cell technology, we tried to do this. We know technology, and we were able to produce black silicon. But you know, when you are doing black silicon, you are generating really very huge surface recombination. Just because of this nanostructure you are putting on top of it. And this is becoming quite an issue, just because passivation of such surface is of really serious issues. Therefore, well, it's a really good idea. Yes, of course, it's extremely highly efficient way to collect all energy which is going into device, and this is I hope somehow will be solved. Another point, perovskites. Actually, I was very fond of this technology. We were participating in number of activities trying to find way to integrate perovskite devices with silicon, but actually main issue is durability of these devices. Actually, I don't know still, after almost 10 years development, device which will survive more than few months. Okay, there are some, let's say, reports about longer life span of these devices, but it's some tricky issue. We are prepared to integrate with silicon solar devices. This, let's say, when it came into reality, perovskite models, and our idea would be to start from 4 contact, 4 terminal devices, just because if you want to replace that perovskite layer after few years, when silicon is surviving for 25-30 years without any problems, then you need to have some simple dismantling technology to replace this device with better ones. Okay.
Thank you.
Did I see a hand raised by Dr. Nazir Basha?
Okay, please.
No, madam, I didn't raise my hand. I just clapped for the session.
Ah, okay.
Okay, thanks.
So we have 1 minute. I think we can move on to the next presentation.
Okay.
Oh, Sarah, did you have any questions? I guess no. Since it was our only one speaker from photovoltaics industry, so I guess maybe more questions will raise, and everybody can write down their questions and ask them after all presentations are finished. We will have time for that. So, and now I would like to welcome Robertas Grikšas, CEO of Ados Tech, who will tell one case of how he applied his laser technologies for photovoltaics industry. Please, Robertas, you are welcome to present.
Hello, can you hear me?
Yes.
One moment. I'll just... Can you see presentation?
Yes, only we can't see you.
Oh, okay. So it's okay. I have very sensitive know-how behind my background, so I can't show it at the moment. Okay, I guess. Okay, so I'm Robertas from company Tadas Tech. We design and produce thermal and night vision devices, and because of that, these devices and the vision they provide, we as well have some touch on solar cells and inspecting on them. So I will try to walk through of some methods which can be used in order to see the defects or malfunctions or faults of installed solar panels and cells as well. So it will be like a walkthrough from through the possibilities how to check the working devices. So most common problems which are listed by the users and manufacturers are all listed here. So it's like potential induced degradation. It's called in short acronym PID, which occur due to voltage difference between the earthing and the solar panel, and its primary and ends up by producing partial voltages, and it degrades the whole panel in longer term. So it's one of the common issues, but which can't be detected that easily. So we'll get to that later. So it's one of the physical, technical issues is the lamination internal corrosion, which happens like over time because of the environmental and weather conditions, etc. The next one is electrical issues, which of course happens while installing, or maybe there are some left manufacturing mistakes, but these are like more easily maybe detected. The next one are glass breakage and micro cracks, which can occur during logistics, transportations, and sometimes handling while unloading, and etc. There's also as well hotspots, which I showed on the right of the slide, which is hard to notice with your naked eye, especially when you have like reflections from outside, but it can be seen with like the other spectral regions, and it occurs usually in production and changing of the seasons because of UV exposure and etc. The next one is our how to say nature habitats like birds, snails, which leaves, I mean, some of their parts on the panels, as well traffic pollution, which may occur in more densely trafficked areas, and that can pollute your solar panels. The next problem would be like inverter problems, which may be connected with the connection and installing, and the other one is insulation failure, which is most difficult to see because it's more connected how well things are built, and some of the places you can't see while they get to you, and etc. And yellow and browning is more like accumulating effect, while solar panels are being used. So during all the seasons, the materials degrade, and then you can see some due to UV radiation from the sun, some changes of the color, and it's due to materials and aging. Okay, so I will look through these methodology slide by slide. Here is like listed like visual inspection, which is very common. Thermography, it's a thermal image. Lock-in thermography, it's the same thermal imaging, just you have to have some synchronization between taking the photo and exposing it to environment. Electroluminescence is technology which is used in reverse of elements, a solar panel current switched, and it works like LED, where you expose infrared. Then it's the same daylight luminescence, just during the daylight. Then it's UV fluorescence, IV characteristics, which means current and voltage characteristics, and the most common one is multimeter measurements. Okay, so visual inspection. So this is the most trivial and still most effective method, especially with the people who is trained and able to detect module failures by simply looking at them. And if you have an experienced eye, it's much easier to do that if you as well know common problems. So these can be done right away when you get the panels before installation, and usually it's already done in a factory. Thermography. This is common methods, and we as company are more used to that because we produce thermal devices, and time to time we had a chance to help to determine the problem for some of our customers or friends who likes to check if everything works properly, even during the acquisition of some parcel with solar panels. So this method works direct and indirect heat, where photovoltaic modules is turned on, and you can it's very fast and contactless. You can perform during normal operation in good or bad weather conditions, but usually it requires like 600 watts per square meter of sun irradiation, so you can distinguish the temperature differences. And usually temperatures of a single cells which is working properly and intact may vary about few degrees of Celsius. And if for any reason the electrical resistance increases, you can see that significantly rise of temperature, which allows you to see where the possible defects are coming from.
Sorry, Robertas, how many slides do you have left?
Oh, only 4.
We already used the question time, so you have 1 minute.
Okay.
And then
Okay.
Invite our speaker. Okay.
Yeah. Okay. Okay. So I'll be short. So lock-in thermography is usually the same as previous one. Just you have to do synchronization. So it's can be performed at daylight as well as nighttime. The module is pulsed with the current feed and synchronized with taking the pictures of thermal images. And in contrast, to the states of in pulse mode and in not, you can see the high contrast between the images where you put under the stress the element, and you can see these blemishes of your solar panels. Electroluminescence is, as I mentioned, the most common as well for indoor use, because you reverse the bias of the photovoltaic panel, and it works as a LED, and then you can see the emitted infrared light. And using this digital camera with VR filter or image intensifier, you can detect that illumination. Daylight luminescence is the same method, just using indium gallium cameras, which are very sensitive, more than silicon cameras, so you can watch the same effect just in daytime. UV fluorescence is a method which uses UV cameras, and you can see the defects which happens because of long term for solar panels exposed to sunlight. So you can see with illuminating with a UV source or the elements, or using a UV camera with a filter, how these elements look under UV light, and you can see the defects which accumulates during the use of the elements. And last one is multimeter measurement and IV characteristics. The IV is related to current and voltage, where you can do direct measurement with a multimeter, seeing what is the power produced by solar panels. And in IV characteristics, you can measure the starting parameters of your solar cells, and then you can monitor after some time how it acts later on. So that's it. Sorry.
And that's okay. Thank you, Robertas. And I encourage everybody to write questions in the chat, and Robertas, you can answer there, or we can discuss after all presentations. And now, Egidijus, you are welcome to present. Egidijus, CEO of Evana Technologies, will talk on various applications for semiconductor industry.
Can you please switch off presentation? Maria, can you switch off presentation of?
Yes, I did.
Thank you. Thank you very much. I will share my screen. I hope you can see. So, just a moment. We are a company for some semiconductor material dicing technology development, and I will show two kinds of technologies, for mainly dedicated for silicon carbide. This is one thermal laser cleaving technology, and some other group of material, silicon, sapphire, lithium, Niobate, Tantalete, Quartz glass is icicle technology. And you can see our really activities mainly is for laser processing technologies dedicated for industry. We are working also with some other projects for laser pinning, laser waveguiding in silicon, and we are developing some freezer series optical engines for processing of semiconductors. Here you see some list of materials, which is really, we already try and get good results for dicing: silicon, sapphire, quartz, glass, lithium, niobate, tantalete, and laser cleaving technology for dedicated for silicon carbide. And we are working also for gallium nitride and diamond application for these materials. All these two technologies we protected by patent portfolio. It means for icicle we have in 6 countries already issued patent, and for thermal laser cleaving we also have 6 countries issued this patent. For this technology patent protection. If we start from silicon carbide, because this is only one material for this technology for the moment, and silicon carbide, as you know, is quite promising material for high power and high frequency, radio frequency microelectronics, and this is really some future green technologies for electrical vehicles, renewable energy, and so on. So, and next field is radio frequency devices. It means mobile communication. We can see this is silicon carbide for after scribing and after breaking. It means we can make dicing of this material very easy and really not with big limits for thickness of the material, because we tried up to 400 micrometer silicon carbide, and it was quite successful cleaving of the material without any loss of line along the cleaving street. You can see here some after breaking view and cross section of the material for 100 micrometers, I think. Here, and here is another sample which we developed also technology for dicing of the material. When material is coated by gold film, we make this in one pass, in one scribing dicing process for 300 millimeters per second, and you can see here sample after scribing and sample after breaking and stretching. View of the micro scale, you can see here street view and some comparison with stealth dicing and ablation laser processing. We have quite good result in our technology. And here you can see some comparison with another technologies with scribing speed, throughput, station price, station for the year. And if we think that, for example, we need 1 million wafers per year, you can see factory need 21 stations for about 4 million euros and 15 million diamonds, so price and maintenance. And in our case, it's just 2 stations and worth is 1 million euros only, without any big maintenance costs. Next is silicon, also one very big group of devices which really based all electronics, microelectronics. And also you can see our achievements for dicing quality. You can see 0.25 millimeters thickness, 0.5 millimeters width, and 75 millimeters length strip. And after dicing, you can easily break this without any cracking and destroying of this line. So also we can do this round shape dicing. Here you can see examples for 100 micrometers thickness silicon. You can see the line direction shown by arrows, and on the top surface you don't have any damage after dicing, and after breaking you can see very straight line without any cracking, chipping, etc. So cross section of this material after breaking you can see here 100 microns, and really this is zero curve, almost zero curve cracking of the material. It means zero curve cleaving of the material. Next is some few examples for more thick silicon. Also, after dicing, you have no any sign of dicing line. After breaking, you can see line. Here is cross section of 200 micrometers thickness of the material. Here, another side, it means 700 micrometers thickness of the material, and you can see after scribing and after breaking of the material, a straight line. Here you can see cross section of the material, 700 micrometers, and here is two passes for 300 millimeters per second for 700 micrometers thickness of the material. Also here you can see some comparison with scribing speed, throughput, station price, station for the year for 1 million wafers per year scribing, and we have 2 stations for 1 million and 5 stations for 1 million plus 3 million diamonds and maintenance. So again, we win in efficiency and money consumption for the job. Here you can see another material, sapphire dicing. This is mainly dedicated for LED industry, and you can see again after scribing you can see some cracking line on the surface. Here you already can see cracking, and line sometimes is quite smooth, sometimes it's not very smooth, but anyway in the range of 10 micrometers plus minus you can fit easily into the street of LED wafer. Here you have lithium Niobate. It's for some telecommunication devices, material application and optical devices, integrated optical schemes. Again, we make some trial for this material, very fragile and very brittle material, and we get good result for this scribing and breaking, means dicing, and our results really overcome other competitors. Same situation with lithium Niobate. Again, nice surface view after scribing, and cross section also quite good. So also we have some experiments for ultra thin quartz dicing, and we had good result for quartz dicing for 50 micrometers thickness with 300 micromillimeters per second velocity. You can see surface view. It means that you have no any damage by laser, just you get crack from inside, and this is cross section of the material. So that is it, and really we open for collaboration and for some integrators in these applications for these materials. Thank you, and your questions, welcome.
Thank you, Egidijus, for your presentation. It was very nice. And now we have got one question already from Chris. So do they use any particular optics with axial beam shaping properties like axial beam splitting elements, increasing the depth of focus for the dicing processes?
We use all tricks which really we can apply, and we think that is good enough for our dicing technology. And some optics we do by ourselves. Some optics it means we design by ourselves. Some optics we really order from our partners. So it means that I cannot open any details for this our technologies. But if you would like to have some collaboration and or some kind of business with us, we are ready to discuss.
Thanks for your answer. Do we have any more questions to Egidijus? Don't be scared or shy. Tadas, maybe you have prepared something?
So, Egidijus, you have a long experience working with this material. Do you see a potential for microelectronics market, and maybe what kind of partners you are looking for integration or for some users of your technology? Do you look for some integrators or some, I don't know, end users of manufacturers?
Yeah, I will start from the last question. It means that we are really very interested in integrators, because integrators already have their, how to say, customers pool, and really it's much easier for them to work with us if they accept our technology. And also end users also very welcome. Just question how we implement this, because we not only just technology developer, but also we looking for, we already have some few partners which are ready to make some integration of our optical engine and our technology in their stations. And as what is for markets, it means that I just described two big markets. It means silicon market, which is almost 90% or even more electronics is built on this material. And we found very nice, very gentle, and very, how to say, cheap way to make a dicing of silicon without any damage on the surface. And we are ready to discuss, and you can see even 700 micrometers, it's easy for us to do this. And another big market, coming big market, is silicon carbide and maybe also gallium nitride, which is really dedicated mainly for high power, high frequency devices. And this is somehow coming future for green technologies and communication. So we expect again this market will accept us for our really process.
Thanks for the questions. Thanks for your answers. And now I would like to invite both science and business representative, Paulius Gečys, who is CEO of Lightdensity and head of Laser Microprocessing Technologies Laboratory at the Physical Sciences and Technology Department of Laser Technology. Center for Physical, yeah. So Paulius Gečys, we are ready to listen to you.
Hello, everyone. Thank you for the introduction. So yeah, I come from Center for Physical Science and Technology. and I'm head of laser microfabrication laboratory. So what we do, we develop laser microfabrication processes, like for laser ablation, glass processing, surface structuring, efficient ablation, beam interference patterning, selective metal deposition technologies, and other technologies. We have many kinds of lasers, for example, like CO2 lasers, nanosecond lasers, picosecond lasers, and femtosecond lasers. We also have a spin-off company, Lightdensity, where we can provide services for the companies. Yeah, so maybe now I'll move to the thin film processing of CIGS panels. So why we need to go to PV, it was also already discussed in our so the main, let's say, main type of cells are dominated, of course, silicon PV, and much of the installations are done on the silicon PV based solar cells because they are quite cheap and efficiency is quite high. So when we started in 2009, so CIGS thin film technology was very promising. So it is thin film technology, so you save materials, energy payback time is better for the silicon compared to silicon. We have very light models, and they can be made very flexible. So, and the efficiencies show quite similar to the silicon-based PV. So now I think the record efficiency is like 23.35%. So, but when years passed, all the companies we collaborated and then had some projects actually were bought by Chinese or bankrupt. So now all the CIGS manufacturing is only in China, and they develop some go further developing some new module productions. Okay, so so where do we need to use lasers in such devices? So so here's a CIGS structure. So we have like a substrate. It could be glass or let's say flexible polymer substrate. You have a molybdenum back contact. You have absorber layer, and you have thin transparent conductive oxide, for example, zinc oxide. And you see that the layers are quite thin. So so to increase the amount of light reaching the absorber, you have to make these contacts thin. So, but it's done at the expense of a reduced layer conductivity. So in the case, if you want to have a thin film module of 1 square meter, so actually you are limited by the current of a single cell up to from 1 up to 0.5 volts. That means you can end up with a very high generated current, and you have really high resistive energy losses, and it's not optimal for the device. So what you need to do is you need to divide this large scale module into smaller cells interconnected in series. And in this case, we have a monolithically integrated cells. That means that these cells are interconnected at the different stages of module production line. For example, like here we have like a back contact deposition. When we have like a P1 process where we metallic back contact formation or the division of the cells. Let's say when we have absorber layer and buffer layers deposition, when we have laser stripe P2, where we absorber striping, and after the front contact deposition, we have cell isolation, so P3 one stripe. And what we get is that we have cells interconnected in series, and here some red arrows represent the current flow in this module. So, and instead of one cell, we have like from 100 to 200 cells in one module. So, and this interconnection and scribing is done, of course, mainly by laser technology. So, so the P3 process, we mainly in our research was concentrated on the P3 process. So, cell separation or isolation. So, because this is the most challenging process. Because during the laser processing, I mean, you induce some heat effects. And then this can lead to a CIGS material degradation. That means that you can have some changes in the cell electrical behavior or some additional parallel resistances due to material degradation. And of course, this will affect the device efficiency. So our primary thought that we need to use ultra-short lasers to reduce the heat affected zones and heat effects to the minimum. We also developed some technique where we can optimize our laser processes. We call this like linear laser scribing technique. So we can, basically what we do is we can measure this additional parallel resistance of laser scribe caused by material degradation due to exposure to the laser. So what we do is just scribe some predetermined scribe length, and then measure the IV groove. And from scribe and measure procedure, we can extract some specific parallel resistance values of a laser scribe in a Siemens per meter units. And this is a really good way to characterize our laser process. So we have to keep these parallel resistances to as minimum as possible. Okay, so we used several types of lasers. So picosecond laser operating at fundamental harmonics, second harmonics, and third harmonics. We used a special laser operating at 1342 nanometer wavelength, and a nanosecond laser operating at far infrared, 2500 nanometer. And depending on the system, we use like Galvo scanners or XY stages for the P3 process. Of course, we used investigated two types of P3 processes. So one is to remove full layer stack to expose the molybdenum back contact, or remove only the front contact. And we used full operational single cells from one company, and we scribed in between the contact grid and measure the additional parallel resistances caused by the laser processes. Yes, so of course we've done some simulations as well, how these different wavelengths interact with multi-layer structures. So this is some laser absorption and recalculated temperature distribution inside the thin film structure. So we see that most of the temperature or absorption is made at the top layers or top contact layers. However, we see some diffusion of heat into the CIGS as well. For example, with infrared, mainly with infrared, 1064 and 1342 nanometer wavelengths. You even have some temperature spike at the interface between the molybdenum and CIGS layer for 1342 nanometer wavelength. Yeah, so we see that some of the wavelengths might affect the CIGS layer more than others. So maybe let's now to move to the scribing. So this is upper side is P3 type 1, lower side is P3 type 2 process of all the different wavelengths. So you see that, for example, here we have a molybdenum layer exposed. Here we have some remelting of CIGS edge, and we have undamaged top contact here. So this is just a single side view of a channel. And we see with SEM images with the different wavelengths produced. Again, P3 type 2, we see some the ablation only of the top contact and some modified CIGS layer. And we see that maybe, for example, as for visual inspection, we might say that, for example, picosecond laser green irradiation looks pretty nice, and we see some good results with the P3 type 1 and P3 type 2 process. So maybe let's now go and see how we can how the electrical measurements look like for these wavelengths. Yeah, so we see, for example, with green, so we see that actually conductivity is quite low compared to other wavelengths. Of course, we have even slightly better results with UV for both P3 type 1 and type 2. We see that if we go more to infrared, we have some increase in the cell parallel resistance due to some temperature accumulation inside the CIGS layer. And we see that, for example, with 342 nanometer, we have quite high conductivity values. And now, if we switch from the picosecond laser to the nanosecond laser, but operating at far infrared, we see that, for example, P3 type 1 in this scenario gives a really conductive scribe. That means we remelted the CIGS and we induced some structural changes, and we have really induced parallel resistances, and this is really bad for the cell operation. But if we see for the P3 type 2, where only we gently remove only the top contact, we see actually that the parallel resistance are very low. So it means that selecting proper wavelength for such a multi-layer stack structuring is really important, and it's even more important than selecting shorter laser pulses. So as we obtain these specific scribe conductivity values, so we actually can then model our module performance, taking into account this additional parallel resistances caused by the laser scribe. So we use some PSpice software for the module simulation up to 100 cells, and we see some results for the simulated efficiency of a module. So here we have like a theoretical efficiency, a maximum of 24.74%. It means that we taken some values for the modeling from one article, and we see that, of course, after 100 cell we have some degradation of efficiency, because in any case we induce some parallel resistances. But we see that for UV or green or even 1064 nanometer wavelength, so the efficiency losses are quite low. But if we switch to deeper infrared for 342 nanometer, we see that efficiency losses are becoming higher. And if we even switch to the nanosecond laser processing, so we see what P3 type 1 gives a really low result, so efficiency drops significantly. However, if we use P3 type 2 process. So we see that efficiency is really high when comparable to theoretical efficiency of a single cell.
We have 1 more minute left.
Yes, so conclusions. So mainly, so it's possible to laser structure or let's say selectively remove layers with a laser. So, and from our research, we see that it is really important to proper select wavelength, and it's even more important than selecting pulse duration. So these results you can find in our latest paper. And yeah, thank you for your attention.
Thank you very much for your presentation. And now the questions are welcome.
Okay, can I, Juras?
Sure.
Okay, maybe 2 questions. One remark, another question. Well, we still have in Europe at least one producer. It's Lithium.
Yes, I'm aware, but it's kind of I think Indian bot company.
Okay, but they are still operating, and well, they are open to innovation. Therefore, just use your chances to.
I mean, yeah. So we had a project Apollo where we actually had collaboration with them, and together with Swiss Institute, Bern Institute of Applied Sciences, we actually developed some processes for.
Excellent. And another question: how you see your chances to penetrate market with your equipment?
Yeah, so actually we so in this case I more represent like academia. So in this case we we were together with external partners, and for example like Lithium, we were developing this laser scribing technologies. So I know they are using such technologies for CIGS production right now. So I mean, these technologies are already there in the market. So as for us separately, it's quite difficult to enter such a big market because we have huge factories, and we need to talk to actually to provide such technologies for integrators and sell their technologies, our developed technologies to them, or collaborate, or for the machines to be integrated in these huge factories for cell production. So maybe we are, I would say, maybe too small to handle such such integration.
Okay, my suggestions would be more ambitious.
Yeah.
It's always possible.
Yeah.
Okay, thank you.
Yeah, so yes, as Evana Technologies mentioned, that maybe the best way is to collaborate with integrators, and so because they have their customers, they have their already they are producing machines, so to have a collaboration with them maybe is one of my, I think is maybe the best way to introduce such technologies to the market.
Thanks, and we have a room for 1 more question.
Maybe I can ask one question. Just Paulius, you mentioned that femtosecond lasers are most promising, but in your slides you was using a laser. So maybe you could explain.
Yeah, so I decided to present this part of the research because it was interesting and then really awkward for us. Because we usually thought, okay, we have thermal effects, so when we apply laser, we have thermal effects, and we can degrade, and the absorber layer can degrade. So let's use ultra-short lasers, and we have less thermal damage. So it's obvious conclusion, right?
Mm.
And we did, and we see actually quite good results. But in the end of the project, we just had a laser installed, another second laser for different purposes, operating at these exotic wavelengths, and let's say, okay, let's try. And then the results were very interesting. I mean, because I mean, you have with far infrared, you have a really big absorption, free carrier absorption at the top layers, and you can, and it's really beneficial. So it was surprisingly surprise for us. But since our let's say projects were finished, and many companies are now moved or so the bankrupt or sold to Chinese, so now there's no space to develop further such technology to see. Yeah.
Okay, but do you see that for the femtosecond lasers, also green wavelength is the most promising?
Yes, I would say yes, green or UV. So it depends, because of course we, for example, for module simulation, we took into account only this P-prescribed additional parallel resistances. So you have our effects, which will invent the full module efficiency will be not significantly, but in some extent lower to this theoretical single cell efficiency. So yeah, so I think in the case, yeah, like green irradiation, maybe fourth femtosecond or picosecond laser is the most promising. But we have to look very carefully at these far infrared devices, and maybe there is also really good chance that they can be applied as well. Yeah, but also we have to take into account that we used a parametric device. So again, so are they stable enough and so on? There's a different kind of issues to consider when entering this such a market.
Okay, thank you for a very detailed answer. And now, Laurynas, I invite you to prepare. And Laurynas Čekanavičius is project manager of Porsche for Photonics, a very successful laser micromachining company of Lithuania. So Laurynas, welcome.
Hi, everyone. Yep, just let me start sharing the presentation. Yep, I hope everyone can see it now.
Yes.
Yeah, so I represent Workshop of Photonics, company based in Lithuania, in Vilnius. However, we work worldwide, mostly with semiconductor industries and biotechnology industries. And today I'm going to present and discuss technologies and processes that we have for glass, sapphire, and photovoltaic devices machining in a broader sense. To whom that are not too much familiar with our company, since we are not that significant in the size so far, but have extensive experience over years. So we are almost 20 years active as a company, and all our staff are coming from the engineering and scientific background. That brings us into the quite nice position for competitors, since everyone has their own expertise, bringing the knowledge into the company and summing up that with the experience that we have working with our customers. We have quite a few technologies and quite deep development in some specific fields that I'm going to cover later in the presentation. skip that one. So we are also working with associations and try to communicate our capabilities that we have in-house. So just wanted to mention that we are also proud to be members of Toolas, quite recently joined, and seem to be working for us quite well so far. Why it's worth working with Workshop of Photonics as a company, having a deep and extensive understanding on our customers and how they operate and what kind of the solutions and at which time they're looking for. We have found out and concluded that we must work with them in every step on the development, starting with the initial concept, going all the way to the system development, installation, and their facilities. So specifically with the semiconductor industry, even big players have the processes that they look for the partners to test, to develop, to bring the feedback, to conclude whether these are feasible. And once this answer is given, they try, of course, to scale it to mid-size production at least, or have the in-house machine to develop the production further by themselves. That later on, of course, scales to the mass production that we see on a daily basis in consumer electronics, for example. As the company, we develop solutions not focusing on specific materials, of course. Later on, we are going to focus here on silicon, which is in principle the key material in the semiconductors, but WEP is also working extensively in other materials that are used in this segment. So that would be glass, sapphire, as for example. We have glass cutting and sapphire cutting technology for zero curve cutting to dies, for example, wafer level package electronics, and later on bring those electronics into the packaging steps and to the consumers eventually. Other processes that we see to be necessary for semiconductor market is drilling, as for example, although here we mentioned glass and sapphire, it's also applicable for silicon. Even big players have demands for specific silicon glass sapphire wafers machining to add a few vias, blind vias, trenches, and so on in the wafers for their process development and production process too. And of course, recently discussed benefits from ultra-short pulse lasers. We do selective modification, selective layers removal for also various wafer level packaging applications where this process is a must-to-have step after extensive coating and wafer preparation steps. So going into details for glass and sapphire cutting, the technology that we have, and I already mentioned, it's zero curve cutting technology that allows maximizing the material use, so you don't waste the material and you don't have debris on your wafers after the cutting. It's well considered as a preferred solution, so to say, by the users, because you protect your own production. You don't have to add additional washing steps, and of course you have maximum efficiency and maximum speed, so that directly concludes to the best price ratio that you can use and offer to your customers too. In the screen you see sapphire and also glass cutting examples. Specifically, glass can also be tempered. This is not the limit for our technology. It can be can be of course tested, case by case, but all sorts of shapes can be cut out from the wafers, Sapphire wafers, glass wafers. Just want to emphasize this. We don't have limitation to use only square or rectangular shapes. It can be also circular, elliptical, and so on and so forth. Limitation in glass thickness. So far, we have successful results for up to 3 millimeters single pass glass cutting. We consider that not to be the final limit to us. It's just in one step further in the process of development. Once we reach higher thicknesses in single pass cutting, what considers thicker samples, of course, we can cut not single but multiple passes as well. So we don't have really a hard limitation in thickness from that perspective. Irregular shapes, I've covered that. Yep, the final note is that the key benefit from the technology is the speed that is crucial for every semiconductor company that strives to actually grow and to decrease the price, so they would be able to cover larger market and have better sales from their perspective. As mentioned, our company develops not only the processes or deliver the services, we also integrate and install the systems into the production lines and R&D centers for semiconductor industry. And that same applies for the glass cutting based technology for glass cutting workstation that we have. Compared to alternative technologies, since our own laser dicing method is not the single solution being present in the market, we have unique capability to work with relatively thin glasses, which I described as single pass cutting, but we also have unique capability to deliver ultra thin glass and sapphire cutting. So specifically, glass can be cut essentially as thin as it can be made by the suppliers. And surface chipping, we also have the glass separation after the dicing solutions that we offer to our customers, and not one, but a few solutions. So really depending on the application technology and wafer structure that's being diced, we can propose our knowledge and advice what would be the best solution to go with afterwards. Other methods and other processes that we offer based on glass drilling, as for example, we develop our own products, so specifically glass carrier wafers that are used as for temporal bonding and transferring the wafers in the production lines at semicon industry. We have unique technology to create millions of holes per single wafer at very low cost basis that are crucial for to be competitive and accepted in the semiconductors market. We also produce guide plates for the probe cards. This sector is specifically focusing on ceramics to be used, which is a sort of conventional solution that was accepted over the years. And the single challenge they have is how to decrease the dimensional sizes in the holes. So you always want to have denser contacts, so you go for the thinner probes, and of course then you have to go down to more holes, smaller holes, and more holes in single guide plates. Our solutions, they can be done with the glass or compared to what can't be done, and we therefore are able to offer already down to 30 micrometer holes per probe card, which is essentially impossible to do with ceramics on cost reasonable basis with alternative technologies so far. And other limitations that we have, well, they're not really crucial, so to say, since aspect ratio limitation in glass is 1 to 100, which is normally not nearly that's necessary. So we're really looking forward to test the limits and see what and how works the best. Typical hole diameters are down to 20 micrometers. Working on case-by-case examples, these are possible to be even lower. Typical size tolerance for holes in Sapphire, silicon and glass too, are roughly around a micron. Also, depending on the case, these can be even higher tolerances. So really the technology that brings you to the edge on what's capable to what's possible to be done, at least these days. Alternative processes that we find to be requested by our customers in semiconductors, so selective layer removal, grooving, blind holes, all are maybe not requested on production basis, but at least are discussed and looked for development processes. So it would be really interesting to learn more and find out more where and how they're planned to be developed to production processes in the future. So this is one of the things that we are working on now to find out the key benefits and challenges that these companies have today. And what other presenters have already covered, it's photovoltaic devices. One of the sector that our company works in, semiconductor market. We over the years have a few successful cases working with conventional photovoltaic devices, specifically focusing on efficiency development and opening the contacts in solar panels and working on efficiency improvement. That was the key challenge by our customers, but since these elements were developed further, the main focus for our company so far is thin film based photovoltaic devices, and we are developing a process for scribing these panels, so to say, something really similar to something really similar to the solutions and challenges that the last presenter had. Differently, we focus on the machine building compared to the development in the process at this moment, since key challenges are clear and our customers are looking for implemented solution that's already broadly discussed in the scientific publications at this point. So our company is offering laser scribing workstation to do this scribing process. Mostly we are offering UV lasers, so 355 nanometers wavelength or 343, depending on which specific laser model is chosen by our customers. Limit in positioning size so far is 300 on 300 millimeters, based on the size processing that our customer have, but that can of course be larger if the devices are planned to be used in larger dimensions. Here you also see the typical accuracy and repeatability values on the positioning solution that we're offering, but as our company has capability to customize these workstations, we can also have a discussion which exact parameters are necessary and find out the solution that's required for the specific research team or specific production team that's looking for this workstation. Uniquely, we have capability to adjust the focusing, not only manually, but we can have autofocus solution added to the system. Also, we have machine vision system integrated in the platform, so we can have visual recognition on the alignment marks that would simplify finding and working with these elements during the scribing process. System is fully integrated by us, so we are also offering our own developed software for full system control. So that same applies for single company support after sales procedure. And here you can see some, sorry about that, some of our current clients. Some of them come from with their own specific backgrounds, but we see a high demand in semiconductor industry and really broad scale of the tasks that we have so far. Thank you for your time.
Thank you very much for your presentation. And now, please raise your questions if you have.
Hello, this is Benjamin speaking from Evana Technologies. Thank you very much for the interesting presentation. The slide where you showed the solutions for semiconductors, are you also working on USP ablative? Because you showed a lot of non-ablative stuff with the zero curve loss, and yes, we're familiar with this, but I think the market itself is a little bit saturated. So it looks like the filament is offered quite, from many companies, and it has a drawback that we have to have a transparent curve. But the trend in the semiconductor does not really point to a transparent curve. So metals will become more important. And here I was wondering, are you also investigating ultra short pulse ablative dicing? Because this is where I'm looking pretty intense in it. And if so, what is your point of view on the beam guidance? How would you set up such a ablative ultra short pulse dicing system?
We work on this process as well. It's just, of course, during limited time, we discussed limited methods for presentation. So for ablative process for scribing and cutting different materials or a single not transparent material, we have essentially two types of the solutions. So one is developed to have as high speed as possible with sacrificing the essentially perpendicularity in the cutting line. So you probably would have larger opening on top and slightly narrower opening at the end of cut sample. Another method that we are using ourselves, it's control taper cutting, where you want to have nice cut edge after the process is finished. So you don't really want to have sort of this kind of angular side of the structure that you cut. So these are sort of two types that we have. But everything that relates to the ablative processes, key challenges we see in question whether quality versus the speed. So the speed usually comes first. So this is really something that we're working on now.
Yeah, with speed, I mean, I understand the benefits of the non-ablative dicing, but we have many products where I think this is not possible to do non-ablative. Right. But if you do non-ablative, how do you then do the cleavage, the cleaving? Because let's say you have Sapphire, and you also showed that you can do more or less free forms. I mean, usually dies are clear with four corners, but assume we have a different shape. How can I then finally get the pieces out? How do you do the cleaving? Do you do it by tape expansion, or what's your idea then for this?
For what we have now for the dicing process that we have, we separate. One is either using thermal selective modification after the process to induce self-separation. It can also be done on tape, perhaps usually combining both, or it can be mechanical braking as well. Depends on the coatings that you have, if they are present. Depends on the structure, whether that's circular, whether that's, you know, really everything comes into play. If we are talking about small pieces to be separated, tape is usually what we recommend.
Okay, thank you very much. Last question: are you offering also marking solutions like wafer marking? Do you have there? Have you looked into?
Yes.
And are you able to provide a tool for wafer marking where you can handle wafer? Okay, very good.
Yes, it's well, what's having all the range of the capabilities from ultra-short pulse lasers. We try, you know, to emphasize and show benefits in unique processes. Marking in some cases is done by alternative laser sources, which we also have in our company. It's just you know, hard to cover everything since we are not limited in the process, not limited in the material. So try to yeah, thank you for your question. Really something that I haven't covered in the presentation.
Thank you very much.
Thank you.
Thank you. Who else would like to use the opportunity to ask Laurynas questions?
Maybe I can ask a question about the photovoltaics. Do you have any experience with the crystalline silica wafers processing for solar cells, and which process, if yes?
We had, no, I think it wasn't crystalline silicon. We had one case working with the space agency to have some uniquely shaped holes, blind holes, sort of grooves actually making, but that's no longer active. So really have most experience in scribing process so far. Of course, we look for other challenges and expand our customers range in this specific field, but so far actually I'm pretty glad with what we have now. One of these systems for the solar panels marking will be installed this year in Italy. So this is really the area that we are exploring, and we have some successful results already.
Thank you.
Thank you.
Thank you. So Laurynas, I'm sorry, I will stop your sharing so that we could have a general discussion. And I think we also had one question to Paulius from Tadas. Yes. Can you please explain what?
Yeah, it was already answered.
Already. Okay. Okay. Sorry. So now there is a room for any questions you have to any speakers.
Hello.
Before I go on mute, I just want to make a note that I think there was question to Robertas since he had limited time in presentation. So I think we can go to that one back afterwards.
Yeah, it was answered. Who didn't see? Robertas wrote that we offer IR cameras and viewers for possible.
Yeah, maybe Robertas could explain in more details what experience do they have with these imaging systems.
So speaking about actual experience, so we did some measurements and tests in-house regarding solar panel tests, detecting mechanical damage of alone cells as well as the whole panel structure. And we did that in thermal as well as in electroluminescence mode. So we as well did some cooperation with BOD, Baltic Optical Discs. They manufacture solar panels, and they used our equipment for their tests and robustness of their produced solar panels, where they use new technology, where they can strengthen the flat surface of the panel, so it can resist heavy loads from any type of like impact and etc. So you're welcome.
Thank you, Robert.
Do we have any general questions for the audience to discuss about?
Hello, can you hear me?
Yes, Paul.
Thank you. Hello, my name is Paul. I'm from Lazea company based in Belgium. I had a question for Laurynas about his workstation. Laurynas, you said that you have the ability to have no stitching areas on your machining patterns. Does it mean that you are using IFOV or infinite field of view to process patterns larger than the field of view of your lens in some case?
Yes, that's correct. Of course, it can be the lens to be used as large, having as large scanning area as the product you're going to mark scribe yourself. But we also offer the infinite field of view function.
Okay.
Thanks. So how about those general questions?
Are you hearing me? Sorry.
Yeah, actually I could hear you.
Maria? Okay, sorry.
Do you also hear Paul?
Yeah, thank you very much. Thank you for your reply.
Thank you.
And we have here Skirmante Balagentiene. Do you hear us? Skirmante is representative of Lithuanian Photovoltaics technology cluster. So maybe Skirmante, you took any ideas of how laser micromachining technologies could be applied for your cluster companies?
Hi, thanks for the presentations. Just as Juras told,
Sorry, I can't hear you.
should how we could interact between our two clusters.
I think that was bad internet connection. I couldn't hear the start. What did you said? I think we can continue discussion on our clusters collaboration later on, and to discuss it in detail via some meetings.
Yes, of course. As I said, and Juras said, maybe thin film technologies are more laser pro, in using lasers, but we should discuss more and
Yeah, okay. Thanks, Skirmante, for your comment. And I'm very glad that you and your cluster representatives has joined this meeting. So, Tadas, maybe you have some closing remarks or some closing discussional questions to everybody.
Yeah, so maybe some just closing remarks. I think we got some information about the general technologies are used in Lithuania, about the production. We got some maybe ideas for the companies or participants for the new cooperations, for the new projects. So you are very welcome to contact Maria and get contacts of all the participants, and Maria will probably share slides of this seminar.
And also recording of a seminar if you have missed something. It will be shared via Toolas social media channels.
Yeah, and I believe that we could find successful cooperation in the future. I believe that you got some new ideas for your own companies or institute development, and I hope that these technologies, laser technologies, could be developed together with the Toolas cluster companies. If you have any needs for cooperation, so please contact Maria, and thank you very much for your attention.
Yeah, and to finalize our meeting, who doesn't hesitate, maybe you could show up in the screen and I could make a nice screenshot to memorize our nice meeting and to share with others. Yeah, maybe a little bit more faces would be nice. Yeah, a couple of more. Yeah, thanks. So now I'm making a screenshot so you can look beautiful and smile. Yeah, so since we still have like 3 more minutes, maybe somebody would like to add something to close the event. Maybe some impressions, some ideas. Yeah, if we don't have anything else to add, so then I would like to thank you a lot to everybody for being the guests and speakers of this event. And I hope Toolas will continue with this micromachining applications, and we are planning some events in autumn. The topics are automotive, precision optics, and consumer electronics. So follow Toolas LinkedIn and Twitter, and you will hear the latest information of our plans. And if you have any collaboration ideas, so please contact me or companies directly who spoke today. And yeah, that's it. And wish you the great hot summer. Bye-bye.
Thank you.
Thank you.
Thank you for the meeting. See you. Bye.
Thank you very much. Bye-bye.